Yesterday, when I was talking with some of the folks here over lunch, I just had some questions about what is their expectation from such a conference, and in particular my talk. And some of the folks were very excited by the fact that there will be like packet sniffs, hex terms and things like that on the board. Some of the people said that, well, we can do that in the privacy of our homes or offices, and we would like to focus more on just the general SCADA area. So what I'm going to try to do today is sort of keep a balance between packet sniffs, hex terms and things like that, and also cover the generic SCADA aspects. So how many of you really know what does SCADA stand for? Well, that's exactly accurate. Supervisory, control, and data acquisition. The whole SCADA story, for me at least, it started in around 2005 when one fine day my boss came to me and asked, hey Amol, do we have signatures to identify SCADA vulnerabilities? So to give you a little bit of background, what my team does is we create vulnerability signatures to identify threats, missing patches, possible exploit vectors by which an attacker or a malicious user could break into your system. It's an automated system. And usually we write signatures to identify them. You can sort of compare them to antivirus signatures, only these are vulnerability signatures. So this was 2005, Stuxnet was non-existent, and actually the code which exploited, the code in the Microsoft products which was exploited by Stuxnet was not even written. I knew about SCADA a little bit, but I was in no position to add signatures for those. So I said, well, okay, give me some time and we'll research on this SCADA stuff and get going. So I started talking with people in the industry and to customers who had SCADA systems, and the more I talked with them, I found out that everyone has a different nomenclature for what SCADA is. Some people call them as DCS, distributed control systems, industrial control systems, or SCADA systems, supervisory control and data acquisition. And each of these have some subtle differences in what they really are. But for today's presentation, we will consider all of these, I'll just consider them as SCADA. So at this point, I would like to ask you, like, what are the typical things that come to your mind when someone says this word SCADA? What came to my mind when people talked about SCADA at that time was something like this. Electrical distribution systems, the electrical grid, power transmission plants, oil transmission pipelines, water transmission pipelines, wind turbines. These are all examples of SCADA systems. As a general guideline, what I sort of do is these SCADA systems are pretty distributed, and if you like sort of try to hug one of these, you would end up hugging an entire country or even an entire continent. The systems at the bottom three systems, they are typically called as industrial control systems, where the system is huge, but it's still confined to a small plant, or it could be a big plant, it could be multiple plants, but it is confined to a plant. So the examples that I have is like a donut manufacturing plant, where all these donuts are automatically fried and you get your Krispy Kreme donuts, or automobile manufacturing plant. So I was wondering why in 2005 my boss wanted me to write the SCADA signatures. So I went on investigating, and there have been a few accidents in the SCADA industry. The link that I have mentioned here, and at the end of this presentation I'll give you a link where you can download all this, so you don't have to write this down, or is a US government website which details on liquid pipeline failures, on if it was operator error or if it was a system error. Another link is a similar link from NERC about power failures. And there have been a lot of accidents in SCADA for the last 30, 40, 50, 80 years, as long as these systems have been there. But still, that was not a reason enough to start going after SCADA. There have been cases of vandalism, and the example here is actually pretty close to where I live, is where some of the vandals, they just destroyed rubber gaskets of some electrical power distribution hubs, and they caused a power outage. So I said, well, okay, that's a good enough reason where power companies or these oil transmission plants would want to protect themselves against vandals, and that's why maybe they need the SCADA signatures or the ability to identify SCADA threats. There have been a lot of insider threats where someone who is in the plant goes rogue. And the example here is one of the employees, he was fired from a water treatment plant, a sewage treatment plant. And the very next day, since he had all the details of the plant, he just emptied out all the sewage in Australia, actually in parks and in rivers. So that was really a bad thing. So I said, okay, well, that's the reason I guess SCADA is getting a lot of attention. But what I missed was at that time, this word didn't exist. How many of you know what the APD is, or have at least heard of it? So a lot of you have heard of this term. So advanced persistent threats are, I think, today the most pressing reason for securing SCADA system. These are typically used for espionage. They are used by states. And who can tell me what's the number one example of an advanced persistent threat in SCADA? Stuxnet. Great. So, well, nice to hear that response. So Stuxnet, as most of you may know, it was a virus which was targeted to exploit Siemens PLCs, and then not just any Siemens PLCs, but some Siemens PLCs which were used in nuclear power plants, and not any nuclear power plant, but very specific nuclear power plants. Now, I'm not going to go into the politics of it, but these are some of the, as I said, the most pressing reasons why the industry is right now focusing so much on SCADA. And the link that I have here is for the analysis of the Dooku worm, which they said is basically so close to Stuxnet, is that the writers of Dooku have to be same as that of Stuxnet. Now, Dooku doesn't really do much damage as Stuxnet did, but it basically propagates and just finds information about your network and what type of SCADA software and hardware is present. So I said, okay, this is the reason I guess my boss is wanting me to find, or he wants my group to write signatures for these SCADA vulnerabilities. But so usually what happens in my group is whenever there is a new software or a new hardware or a new database or a new phone, and we have to add signatures for it, we get that software, hardware, database, whatever it is in our lab, and we sort of bang on it till it breaks, and possibly find vulnerabilities, create signatures for it. But from some of the pictures that you saw earlier about SCADA systems, those pipelines, those electrical power transmission plants, it's impossible to get that type of a system in your lab and try to write signatures for it or try to exploit it. So what we decided was we sort of created a framework where we can take any of those SCADA systems or those DCS or ICS systems and plug them in this framework, which will help our engineers in better understanding of what the SCADA system is. So on the left side is the field, which is basically all the systems or all the sensors or things like that, which could be thousands and thousands of miles away from the control system. And on the right-hand side is the control center where operators would look at alerts and act on these alerts. So let's take a detailed look on each of these components. So as I mentioned, on the left-hand side is what is called as data acquisition. So what happens in data acquisition is there are sensors, there are meters, there are field devices which collect information. And some of the examples that I've shown here is a photo sensor. What it does is it finds out how much light is around it and converts it into analog signals. There is a pressure sensor which similarly finds out what is the pressure of water or whatever liquid that it is in, or even air pressure, and converts it to analog. And the last one is the temperature sensor, which sort of which sense what the temperature is and then converts into analogs. So these are typically data acquisition components, also called as I/O. They have a two-way communication with data conversion components. So these data conversion components, what they typically do is they convert discrete measures or analog measures into digital format. So they consist of PLCs, RTUs, IEDs. PLC is a programmable logic controller, RTU is a remote terminal unit, IED is an intelligent electronic device. And they sort of typically look like this. It's PLC, it's an IED, and it's an RTU. They are usually mounted on these poles, electric poles, where they convert whatever discrete input they have received into digital. Now this data conversion component has, again, a two-way communication with the end master unit or the SCADA unit using various communication techniques. So it could use a wired or wireless communication, it could use Ethernet, it could use radio, but there is usually some communication means using one of these communication protocols to talk between these remote units and the master unit. It's said that there are more than 100 SCADA protocols, open source, proprietary. I have not been able to count all 100 of them, but I believe there could very well be 100 protocols. Here I have mentioned only the most famous ones: Modbus, DNP3D, Tejas, OPC. So basically the remote unit communicates with the master using one of these protocols. And at the end is ultimately your presentation of end control or the SCADA master. So it looks something like this, where there is an operator in a factory, he or she is looking at all these alerts which are happening in the factory, and they can act on those alerts, on what's happening. It used to be more or less of these proprietary systems, but now they are mostly Windows-based systems with Windows-based UI or HMI, which is the human machine interface. So we said, okay, great. Now we know a little bit more about the SCADA systems. We can sort of plug in any of the system and divide it into these four components. Where are the threats? So how do you analyze and where the threats lie? So we assigned each of these components to various people to do a little bit of investigation on those. So there are some threads which are between I/O and remote. So between the communication between this and this. But these threads mostly require physical access. So an example of such a thread could be that there is a sensor and you go and vandalize that sensor. Like the example that I gave you before, that some vandals, they came and they just destroyed the rubber gaskets on electrical power poles, causing power disruption. So this, most of the threads here require physical access, as these sensors, meters, and field devices are many times far off in the field on some electrical power line, some gas pipeline, and so on and so forth. Another thing is that field equipment does not generally contain process knowledge. it contains knowledge like valve 16B or breaker 9B. So for example, if you climb a power supply line, or you will, unless you know what that particular sensor does, it is generally very difficult to guess what will happen if you disturb that. You could sort of randomly vandalize it and see what happens, but without process knowledge, without the knowledge of the bigger picture, this usually causes only a nuisance disruption, like the example that we saw earlier about vandalism. Currently, we are not seeing a lot of threats in this area, but who knows, maybe in the future, when the process knowledge is really well known, we could start seeing a lot of threats where someone goes and just replaces a sensor which gives wrong information to the remote unit. So we said, okay, currently we are not seeing a lot of threats here, and these are mostly physical threats which are not, which cannot be done remotely using a network or anything like that. So then we focused our attention mostly on threats which are communication threats. So once the analog or discrete signals are received from the sensors to the PLCs, they are converted into digital. There is this communication layer which is used to communicate these signals to the SCADA master. So an example of one of the threat here is that you could manipulate a field equipment processor directly. So here is a FEP, you can directly manipulate it, and the output of FEP is the input to HMI. So what happens is, if this is telling you that, okay, the pressure of water is so and so, you can directly manipulate it so that in the HMI, in the operator's console, you see a totally different pressure, and then the operator says, oh, the pressure is very low, let me increase the pressure. But in reality, the pressure is not that low, so it increases the pressure even more, which causes it to burst or something could happen. So that can happen for communication. And then there are, as I mentioned, at least 100 different protocols in SCADA. And now we come to more of a juicy part, or the part which is more interesting, is there are a lot of protocol-based threads in the protocols that are used for SCADA communication. One of such protocols that we will look a little bit into detail today is Modbus. It's a very simple client-server protocol used in SCADA. If you know any simple protocol, Telnet, FTP, SMB, any simple client-server protocol, you can easily master Modbus. It has almost the same thing. There is a Modbus client. The only difference between a Modbus client-server communication and, for example, a Telnet or FTP client-server communication is that in Modbus, the client is called as the master, while the Modbus server is the slave device. So whenever a request is sent from a Modbus client or the master, it goes to the Modbus slave, it's called as indication, and the response when it comes back, it's called as confirmation. So a Modbus client is usually the HMI, or the human-machine interface, where the operator is sitting. So this is where the Modbus client would be, and the Modbus slave would be in the field. And what this protocol is the client or the human-machine interface is continuously polling the Modbus server on readings. So it continuously tells, tell me the temperature, tell me the temperature, tell me the pressure. It is constantly in this polling mode to get data from these sensors to display it for the operator. So let's take a little bit deeper look on what Modbus looks at the frame level. Modbus is a protocol which is around 30 years old. A lot of SCADA protocols are more than 20, 30 years old, even before TCP/IP. So Modbus was not initially designed to run on TCP/IP, and the diagram on the top is a typical ADU, which is the application data unit, and program data unit for a Modbus frame. when TCP/IP started getting popularity 30 years ago, 30, 40 years ago, it was ported to TCP/IP by simply just encapsulating into the TCP and IP packet. So all you can imagine now is it's a very simple protocol inside your TCP and IP packet. So for a minute, let's also get rid of the TCP and the IP header and just look at what you put into the TCP packet for a Modbus frame. What you have here is a Modbus header, NBAP header, some function codes, and then data. The header usually has a transaction ID, a protocol ID, length, and unit identifier. The transaction ID is basically just like any other transaction. If I want to find out, let's say, the pressure of it, I said, okay, my transaction ID for my request is 1, give me the pressure. And when the response comes back, it says, here, this is the response to your transaction ID 1. Or it says, okay, now I'll set my transaction ID as 100, give me the temperature of a certain level, and the response comes back is for the transaction ID 100, your response is this. It's a pretty simple transaction ID. Protocol identifier, which identifies that this is a Modbus protocol. Then length is basically the length of the packet. And unit ID is what unit is this message supposed to go to. So if I just go back a little, here is the Modbus client. It will send the packet here and say, give me temperature on unit number 5. So in a PLC or in an RTU, there can be one or even thousands of sensors attached to the PLC. So first of all, there could be a lot of PLCs, a lot of RTUs, and then for each PLC, there could be a lot of sensors attached to the PLC. So when the Modbus client, which is the master, sends a request, it says, okay, give me the temperature for unit ID 1. So that's basically the unit ID. In the function codes, I just talked about various function codes, like there are function codes like read discrete inputs, read the coil, write to the coil, read multiple registers, write multiple registers. These are the descriptions for the function codes, while there are opcodes which you put into the packet if you want to execute a particular function. And then data is data for that function code. So if you say read 3 registers, then the data would be whatever is for those 3 registers, or maybe the starting address of the first register. If you say read 10 registers, then the data would be the starting address of the first register, so on and so forth. It's specific to the function code. So pretty simple protocol till now. This is an example of a Perl snippet that creates a sample Modbus packet. As we saw before, it has a 2-byte transaction ID. In this case, I have put the transaction ID as 256. Protocol ID for Modbus is always 0. The length of the entire packet, the unit ID, so I want to talk with the unit 1. Function code 3, which is read multiple registers, and then the data for it. So pretty simple pull request. If you copy paste this into a Perl program, it will definitely work. And then you just create a socket and basically send this request on the socket to the Modbus server. So what we see when we send this request is this on Wireshark. Modbus is it's a pretty famous protocol, and usually what we do is when we work on protocols, we have to write protocol decoders for various sniffers because the sniffers don't support them. But Wireshark and I think most protocol decoders support Modbus by default, so we didn't have to write any special decoder for this. So what we see was, we saw that, okay, our transaction identifier, which was 256, went in the Modbus TCP packet, protocol identifier of 0, length 6, unit identifier 1, and we chose function 3, which is read multiple registers. And how many registers do we want to read? We want to read like 5 registers. So this is nothing but whatever went on the packet when we created, went on the wire when we created this packet. And we received the response from the Modbus client, which was, or the Modbus server, which was basically, this is the response, and it read the file registers that we asked it to read. So far, everyone is following me. It's a pretty simple protocol now encapsulated in TCP/IP. You send a request to read temperature, pressure, whatever that PLC is connected to. The protocol doesn't really care what the reading is or what is it connected to. Is it connected to a pressure sensor or is it connected to a nuclear power plant? It doesn't really care. And you get a response. So what's wrong with this? What's wrong with this picture? Usually, every protocol is sort of judged on these three things, right? Confidentiality, integrity, and availability. So by confidentiality, I mean access control, authentication, and authorization is if you say you are this person, prove it to me that you are this person. That's and then access control, which is basically, okay, fine, now I know that you are this person, but do you really have access to the things that you are asking me to do? Do you really have right access to these coils or registers? And we saw in the previous example, the client did not have to do any authentication or authorization, so there is almost no confidentiality here. There is also no integrity here. There are any type of man-in-the-middle attacks possible because it's a pretty simple plain text protocol. You can just change data on the wire in the middle, and those type of attacks are possible. But Modbus is the number one, the most famous, the most widely used protocol in the industry right now for talking between PLCs. It's used more in industrial control systems, in automobile manufacturing plants, and so on and so forth. So we said, well, just having this protocol on your network is a vulnerability in itself. I mean, you don't have to do anything, reverse anything. What the signature that my team was tasked to write was, well, identify that your network is running Modbus and just put it as vulnerability and say that, hey, the protocol is insecure, you have to maybe have some other means of security around it to secure it. So we said, okay, this was too easy. Let's take another protocol. Let's take SCADA scan. So what we are doing today is we are releasing an updated version of an open source tool that I wrote. And what it does is it's a Perl-based tool, and some of the examples that you saw before were from that tool. Is you could scan for all the Modbus installations in your network or even on the internet. So if you want to try to find where is Modbus running in your network, if you have some control systems or on the internet, you could use this tool. So we said, okay, Modbus was too simple. Let's take a look at one of a little bit more recent protocol. So we looked at DNP3. DNP3 is a little bit more recent protocol. It was designed from the ground up for the electrical industry, and almost all of the electrical industry uses DNP3 for communication. It is a little modern as compared to Modbus, as in it has more strongly typed information. In Modbus, you usually poll. Always the client has to poll for, okay, give me the reading. Here, there is an ability where the server can only give readings that have changed. So if you don't get any temperature reading, which means it has not been changed. It has timestamps. So in Modbus, basically, if you say, give me the temperature, it gives you the temperature, you assume it's the temperature for right now, but you don't know the precise time. So that was, the electrical industry couldn't do it without that. So DNP3 introduced timestamps where I say, okay, this is my time, and then when a response comes back, it has a timestamp which says, okay, this was the temperature at that time. So at least the client, the person who calls this knows that, okay, these were the readings at this time. And it has many other enhancements over Modbus. So we say, okay, let's look at DNP3. DNP3 is a layered protocol. It has a link layer, a pseudo transport layer, and an application layer. This is the application layer packet. Now, I'm not going to go into the details of each and every field here, but it is a little bit similar to Modbus, where there is a request header and a response header. In the request header, you have function codes which say read, write, select, same thing. It is theoretically doing the same thing, which is getting alerts, getting information about temperature, about pressure, things like that. And then there is the response header with, again, application codes, internal indications, things like that. This is the transport layer example, where it tries to provide a TCP type of functionality, a little bit the transport type of functionality. And this is the example. This is the packet for the link layer, which has basically a start address of 0564, which is hard-coded for DNP3. Length for the packet, and various control and various function bits. You put your source address, destination address, your CRC, and you can very easily create a link layer DNP3 packet. So this is another Perl snippet that creates the link layer DNP3 packet. As we saw in the previous example, it has this start of 0564. So you put 0554. This is the 1 byte length. This is the control byte, source address, destination address. You calculate CRC here. Well, it's hard coded for this, but in the code it calculates the CRC here. And then again, it's a very simple Perl socket request to send it to the DNP3 server. So when you send this request, what you see is basically this. You send the request to ask for what is the status of the link with these various parameters, and you get a DNP3 unsolicited response saying that okay, the link is up. And again, it has various flags indicating what is the status of the link. So again, without going into too many details, it's again a simple client-server protocol, just a little bit more recent and more advanced than Modbus. So coming back to the same question, what does DNP3 provide? I can see everyone nodding their head. I mean, nothing. I mean, it's still confidentiality, which is basically authentication and authorization. Who you are you supposed to, are you authorized to do this? That sort of capability is not available. Some integrity is available because there are CRC checks, so a very simple man in the middle attack may not be possible. But that's also very, very, very minimal. And yeah, so this is the example of the Perl tool the updated Perl tool that we are using today, which can find your Modbus and DNP3 installations on your network or on the internet. So, well, all is not lost. What happened was in 2007, the DNP3 Foundation came up with an updated standard for DNP3, which provides a lot of things that we were looking here for. It provides cryptography key hashes for message authentication, which is HMAC. It provides key management functionality. So a lot of things that we said were just in the previous slide were not supported in Modbus 3.0 are now supported in the secure version, a newer version of this protocol. So at least that is a very good progress. So we saw some physical threats here, we saw some protocol threats here. There are a lot of threats which directly affect the SCADA master. And the number one threat is that the control system network is connected to the corporate network or sometimes even to the internet. So usually this entire thing, traditionally it's supposed to be air-gapped. So your control system which monitors power or monitors pressure or anything like that, it's supposed to be totally air-gapped from your workstations, your network that you use to send emails or go to the web or do some research. Let's say in a automobile manufacturing company, this network is completely different than the network where you go every day, check your email, do your regular work, then workstations. And in almost all the instances that we saw in our customers or in some of our partners where we just went to evaluate their SCADA security posture, was that on the blue paper or on their network diagrams, yes, this network was completely air-gapped, completely different from the internal network. But in reality, most of the time, when you run automated scans, automated tests, their network, almost all networks were connected to the corporate network or sometimes even to the internet. And you may find it mind-boggling, right? Like a power plant or a gas manufacturing line. Why would it be connected to the internet? But they are. And if you don't believe me, well, now it has reduced a little bit. But when Stuxnet was released, there was a surge in internet searches on Shodan. Have you heard of Shodan? I think a lot of people have heard of Shodan, or some people have not. So basically what Shodan is, it's an online scanner. It's an online free scanner. It just scans the internet for open ports and then grabs their banners and saves it. So you can go online to Shodan, shodan.com, input, let's say, port 21 IIS, and it will give you all the live systems on the internet, or whenever it scanned it, which have port, let's say what we said, port 80 IIS, so which have port 80 open, which have a web server and which has IIS running on it. So you can do these searches, you can right click and just go to that system as well. So after Stuxnet was released, Shodan also keeps a track of what were the top searches that people do. After Stuxnet was released, there were searches for Modbus, for DNP3, for the Siemens PLC, because it also has telnet ports, SSH ports, which gives out banners. So, okay, let me put my little search in for Modbus ports for DNP3 ports. And there were Modbus and DNP3 ports. I'm pretty sure if you go today on Shodan and look for PLCs, there will be still some systems online on the internet that you can access, which I don't think there is any valid reason to have these systems online. So yeah, that was the number one thread that we found in when dealing with SCADA master network. This is something that we talked already, that there is usually no authentication or poor user authentication. So this, actually we call the picture that I showed you, is usually in a secure facility. So when you go in, there are a lot of screens, a lot of buttons. It almost looks like a plain control panel with a lot of buttons and things that you really don't understand. And there is a lot of physical security outside. So when you enter, there could be retina scanners, fingerprint scanners. But when you are actually inside the room, you can just walk over to the terminal and press a switch. Of course, if you go to a nuclear power plant, there will be like 2 guards with you. So you just cannot like run and press some button, and to get there, you have to have certain clearance. But once you are there, the systems don't have any authentication mechanisms to it. And that was fine till the networks were air-gapped. But now, since these networks are connected to the internal networks, your viruses, your worms, they don't have to physically enter the room through the door. If the network is inadvertently connected to your internal network, the worms, just like Stuxnet, can jump from your internal network on these HMI machines and manipulate them directly. So they don't even have to deal with Modbus or DNP3 or try to guess the addresses for PLCs and RTUs. They already have very easy access here, which is the SCADA master. They can just manipulate things on the SCADA master. There are usually no passwords on the SCADA master or default passwords which come from the manufacturer. And I was at a conference in San Diego for SCADA security, and the SCADA owners, they said that the operator has to, there are 24/7 operators in that room. They have to monitor various alerts and act on them. So they say that if there is an alert that there is a fire or some pipeline has broken, as it actually happened very close to my house, they have to act on it immediately. So they cannot input passwords. So that's why they cannot have passwords, or they cannot have long passwords there. But then, I mean, there was a military person at that very conference, and he said, well, no, that's not necessarily true. I have trained my cadets who are like 18-year-old people who can enter like a 25-character long password which is changed every 2 weeks. Of course, being in military, you can enforce certain things. Here, you cannot enforce certain things. But now if you are dealing with critical infrastructure, and as you may have heard in the keynote from yesterday, is by just pressing a button, you can wipe out a nation. I think it's high time people start thinking of these systems as military systems and have and sort of enforce some of these stringent mechanisms to protect them. If there are no passwords, there is no password policy, there is no patching. Now this is a little bit of an interesting subject. A lot of SCADA systems, it used to be proprietary systems, like one that we saw like on the left corner where a man was standing in front of a system. It was a proprietary system. But what happened in around 2000, 1999, 2000, with the popularity of Windows, a lot of SCADA customers asked their vendors, so SCADA vendors like ABB, Rockwell, Honeywell, they asked SCADA vendors to port their software on Windows because it was cheaper. Instead of having a proprietary system, it's very easy to have a standard Windows desktop, and if your SCADA software runs on that, then it saves you a lot of cost. And the vendors, well, they listened to what the customers had to say. They ported their systems on Windows. And what happened later during the time after the 90s, when these systems were ported to Windows, came 2000, after a decade, the age of internet came, and these systems started getting attached to the internet. So now you have a Windows-based system which is attached to the internet, which is vulnerable to all the viruses, worms, everything just like your normal desktop. Instead, it's a SCADA system. So I think this combination of Windows and being connected to the internet has also caused a lot of issues in SCADA. But that brings me to patching. So now the system is run on Windows. And Microsoft, guess what? How many times a month does it release a patch? Once a month. Everyone is patch Tuesday. Everyone is worried. We are worried trying to patch Tuesday signatures too, so that our scanner can identify these vulnerabilities. So when a patch is released, if you are an owner of a big dam, would you be would you really apply that patch there without testing? Never happens. And it's not just that, but a lot of vendors, they have their systems now running on Windows, but they don't provide guidance to the SCADA owners saying that this patch is safe or not. So if I was a SCADA vendor, and if a Microsoft patch comes in, I can easily do in my lab patch it, see if my software works fine, and have it posted online on my website. It's okay, we have tested this patch, at least in this configuration, it is safe to apply. Then it will, as a SCADA owner, it will give me some confidence that I can apply this patch and, well, the power will not go away or something drastic won't happen. But many vendors are not doing that, and therefore the SCADA owners have no choice but not to patch that system because they don't want to take that risk. Other things, well, we saw a lot of systems that have not been restarted in years. So in SCADA, the lifespan of a system could be from 30 years to 40 years to even 80 years. When these systems are built, they are built to last even for like 100 years. And a lot of systems that we have, we saw a lot of Windows 95 systems which were like 15-year-old, and they have not been restarted even once. They have not been patched even once. And when we asked the fellows, they were really very straightforward. They said, well, they are not confident that the system will boot again if they reboot it once. So we had a chuckle there, but it's actually a very serious thing that you have a SCADA system, such a critical infrastructure system, which is running outdated operating system, it's not being patched, and it's not being restarted because there is a fear that it won't come back again. And to circumvent that, there are a lot of battery backups and a lot of other things around that system to just make it work, to keep it running. Since, as we mentioned, a lot of SCADA systems are Windows systems, all the regular IT-based challenges are now here. There are a lot of unnecessary services running. It's now no longer this is a proprietary system. This is a Windows-based system. So you will have unnecessary services. You will have to take care of hardening of the OS and do a lot of these things because of the off-shelf software. So I don't think we have too much time left. Let's go over quickly with some of the challenges we saw. The first one is, I think, the long life cycle of the SCADA system. It's very time-consuming and expensive to basically upgrade a SCADA system or even part of a SCADA system. There are costs for upgrade and difficulties. There is no OS patch guidance from vendors. Some systems are managed directly by the vendors, so if a security consultant is called in to do penetration testing or at least to find what is the security posture, we go in and we see a Windows system. It's okay, we can easily find the security posture of the Windows system, but that system is not really managed by the owner, it's managed by the vendor, so they don't even have administrative privileges on it. They can use the software on it, the HMI software, but don't have administrative privileges. So you cannot even go and see registry keys and do like a simple auditing of a Windows system. And then there are a lot of other SCADA software like data historians and other systems on this SCADA network, which is again Oracle, MySQL, a lot of off-the-shelf software which by themselves have a lot of vulnerabilities in patching. We also saw that there are a lot of internal differences between the IT team and the SCADA engineers. So usually the security team in an organization brings us, or we only do products, but bring in the security guys. And then to even run a security scan or even to do the security analysis, there is a lot of internal, how could I call it in the politically correct way, tensions, which really at the end of the day hurt the security system, the security of the SCADA systems. Wrong mentality, this is changing. I think Stuxnet has changed this. Now a lot of people agree that SCADA is not too obscure. It used to be that people say that, oh, SCADA is too obscure, no one will hack it. But now I think this has changed, and I'll remove it from the slide going forward. So some of the proposals that one could have is a good password policy for access control for roles, strategy for software upgrades and patches, if possible, having SCADA test networks. This is very easy to say, but very difficult to implement because the SCADA test network in an organization would cost almost half of their real SCADA system. So if the crown jewel of your company is like a $10 million SCADA system, but test SCADA system would also almost cost half of a $5 million system. So very easy to say, but nonetheless, I think you could sort of isolate some parts of that system and have that in a test lab. Or maybe if the real system is a very robust system, you could have like a smaller version of that system in the test lab. If you are someone who maintains the SCADA system, demand from your vendors that they give you, whenever the patch is released, they give you advice on if it is safe to apply that patch, demand for secure protocols, and do your work as well. Don't just say that, okay, security MP3 is on my SCADA system. Make sure that the communication is really happening in security MP3 and not in just the MP3. So, and in general, apply your normal IT network management and security strategies to the SCADA network because that will go a long, long way. So that brings me to the final slide. Currently we have the alpha version of SCADA scan, which does modbus scanning and ENP3 scanning, modbus brute forcing. In the beta version, we are planning to add support for SCADA master vulnerabilities. And in the final 1.0 release, we want to have user configurable signatures uploaded to SCADA scan. The reason behind this being an open source and free tool is because no matter how many customers we have, we are never going to see all the SCADA systems. There will always be some SCADA systems that we have no clue about. And by making it more of a community-driven project, what people can do is they can upload their own signatures, their own data dumps to this tool to help other folks, because it's just impossible for us to have all access to all the SCADA systems in the world. With that, well, thank you. I hope my presentation was not too long. This is the web URL where you will find the SCADA Scan 2 and download it. You can follow me on Twitter, because when the next version is released, currently it's really an alpha version. It's really small. It's really just a set of few scripts. But when we add support for detecting HMI vulnerabilities or user configurable signatures and so on and so forth, I always post updates on my Twitter, so you can just follow my Twitter and you'll get all the updates for it. And finally, that's my email address. So that's it about SCADA systems. I hope you got a good overview of what SCADA is, and thanks for coming. Questions?
Regarding the test environment of SCADA, so isn't it possible to write some kind of hardware simulator, small system, which could just simulate and which is connected to the XP? You said XP machines are being used, so software and XP machine, and connected to just some kind of small hardware, which is just simulating SCADA. So that wouldn't cost that much. So is it possible to have some?
Definitely. I mean, we have such hardware in our lab, and if you just Google, you would find some SCADA hardware which supports Modbus, DMD3, all the protocols for like $300, $400. So it's really, really cheap. So yeah, there are simulators available. There are software simulators available which do this completely on software. There are hardware simulators available. So it can be done. It's just that for an organization who owns the SCADA system, it's too much of a geeky developer technical thing that, in my experience, I've not seen an organization doing it. But it's definitely possible, yes.
Are there simulators available for SCADA systems like the HMI system?
So yes, simulators are available for HMI. Simulators are available for all the 4 components that I mentioned there. It's just that it takes a little bit of digging to find them. There are a lot of free simulators available, or you can even buy them. But configuring them requires a little bit of the SCADA knowledge and background. I mean, when we started doing this, we sort of considered ourselves network, remote, or network people who know the network pretty well. But it takes a little bit of getting to know this whole SCADA domain and how to configure this and how to make things talk with each other. But yes, they are available, and you can sort of play around with them in your home as well. All right, thank you. Have a nice lunch.
Thank you, Amol. I'll ask Dinesh to hand over this one to the appreciation.
Thank you.
We're going to break for lunch now. There is a small feedback form attached to the schedule that was given to you when you registered. I would request you guys to please fill it because there's going to be a draw on that. And the lucky winner is going to get a spreadshirt as well as a entry pass for Nalpan Delhi. Thank you.